In this video, we're going to talk about the properties of rational exponents. And I'm going to begin with a review of all of the exponent properties you already know, but we're going to apply them with rational exponents. So let's make a little chart. We're going to write the property over here. And then we'll give you an example of what it actually looks like in practice. So that'll be kind of nice. So property and example. The first property is our product of powers. If I have a to the power m times a to the power n, you should hopefully remember that you just need to add the exponents. So an example from this class, or this section I should say, would be, let's say if I had 3 to the half power times 3 to the 3 halves power. All I'm going to do is add those exponents. So that would be 3 to the 1 half plus 3 halves power. Since they have the common denominator, I can just add 1 plus 3 and get 3 to the 4 halves, which of course is 3 squared. And if you wanted to go further, you can square 3 and get a 9. That's supposed to be a 9. So that's an example of the product of powers. Let's go to the second property. How about the power of a power property? Let's do a to the m power raised to the nth. You know, if you have a power of a power, hopefully you do multiply the exponents. So an example here I'm going to show you is if I have 4 to the 3 halves power and I'm squaring that, what I need to do then is multiply the exponents. 3 over 2 times 2, which is the same as 2 over 1. Remember, if you multiply exponents, you multiply top to top, bottom to bottom, or if you see common factors to both the numerator and denominator, you can cancel them. So I have a 2 in the top and the bottom, I can cancel those, and I get 4 to the third power, which I believe is 64. Number 3, the third property. Let's talk about the power of a product property. If I have a product, a times b, and I raise it to the mth power, I can distribute that power to every factor in that product. So it will be a to the m times b to the m. The example I'm going to show you here is, let's say I have 9 times 4, and we're raising that to the 1/2 power. Now there's technically a couple ways of doing this. I could multiply the 9 and the 4, but that would be no fun because I wouldn't be showing this product, the power of a product property. I'm going to distribute this power of a half to both the 9 and the 4. So I have 9 to the 1/2 power times 4 to the 1/2 power. And if you remember, if you're raising something to the half power, you're really just square rooting. So 9 to the half is really just the square root of 9, which is 3, and 4 to the half is the square root of 4, which is just 2, and 3 times 2 we know is 6. So that would be one way of doing the power of a product property. You guys know about the negative exponent property. If I have a to the negative m power, that's 1 over a to the positive m. And of course, we don't want to have a base that's equal to 0 because we cannot divide by 0. An example of this might be 25 to the negative 1/2 power. If I have a negative exponent, what I'm going to do is move it downstairs, and I'm going to have 25 to the positive 1/2 power, which is just the square root of 25, 5. So the final answer there would be 1/5. Fifth property, we're getting into some of the quotient properties. If I have a to the m over n, you know you're going to subtract exponents, m minus n. So an example of this in practice. Once again, just so we know, since we have an a in the denominator, we would not want to let a equal 0 here. So our bases are non-zero. If I have 6 to the 5 halves power over 6 to the 1/2 power, I'm going to do some subtraction. I'm going to do 5 over 2 minus 1 over 2. And I'm lucky because I have common denominators, so that's going to be 6 to the 4 over 2, which is just 6 squared, or 36. And the last property that we're going to be using in this section is the power of a quotient property. If I have a over b raised to the m, you know you can distribute the m to the numerator and denominator, so it's going to be a to the m over b to the m. Of course, b is non-zero. That's all we have to do. So if I have, let's say, 8 over 27 raised to the 1/3 power, I can distribute that power to the numerator and the denominator, giving me 8 to the 1/3 over 27 to the 1/3, which is just asking for the cube root of 8 and the cube root of 27. And the cube root of 8 is 3. Cube root of 27, the cube root of 8 is not 3. I'm getting ahead of myself. The cube root of 8 is actually just 2, correct? 2 times 2 times 2 is 8. So, and then cube root of 27 is 3. So this one would be 2/3. Let's do some examples in practice now of what we're going to do. For all of these examples, we're going to try to simplify. Okay, so if I can write this out properly. Example 1. We're going to do a few different ones. A. Let's say I have 7 to the 2/3 times 7 to the 1/2. I know I have the same base and I'm multiplying. This is a product of powers. So I'm going to have to add these exponents. It's going to be 7 to the 2/3 plus 1/2. Now this is annoying because I don't have a common denominator. So I'm going to need to get one. I have to add 2/3 and 1/2. So I know my common denominator is going to have to be a 6. I'm going to have to multiply this one by 2 over 2, this one by 3 over 3. And that'll be 7 to the 4 over 6th power plus 3 over 6 power, which if I add the numerators now, I'll have 7 to the power 7 over 6 power. And we'll take that for an answer. B. Let's take a look at this. If I have 3 to the 1/4 times 5 to the 1/3, and I'm raising all of that to the 3rd, well, what I'm going to do is I'm going to distribute that power of 3 to each of those exponents. So I'm going to have 3, and if I have multiply 1/4 times 3, that's just going to be 3/4 times 5, and if I multiply 3 times that 1/3, they're going to just make 1, so I'll have 5 to the 1st, which I technically don't need to write that 1 there. I can just write it as 5, and I'll leave my answer as such. C. I have 10 to the 1/2 power over 10 to the 1/4 power. I have a quotient property here I need to use. I'm going to have to subtract top exponent 1/2 minus the bottom exponent 1/4. Once again, if you are adding or subtracting fractions, you need a common denominator. The common denominator here is going to be 4, right? So I'd have to change 1/2 into 2 over 4 minus, let's make that a 4, minus 1 over 4. That's really going to be 10 to the positive 1/4 power, and we are all set there. Let's do one last example of this type. Let's say I have 12 to the power 1/6 over 3 to the power 1/6, and I'm raising that all to the 4th. What I'm going to do is, I guess there's a couple things I could do, but just to illustrate the power of a quotient, I'm going to distribute that 4 to both numerator and denominator, giving me 12 to the 4/6 power and 3 to the 4 over 6 power. I can reduce that power to 12 to the 2/3 and then 3 to the 2/3. But notice this. The exponents are exactly the same. The powers are exactly the same. So I could write this as 12 over 3, all of that raised to the 2/3. Think about it. If I distributed the 2/3, wouldn't I get back to where I started? I'd have 12 to the 2/3 over 3 to the 2/3. But why I wrote this is I noticed that 12 and 3 were divisible, and I would divide those to get 4 to the 2/3 power. Would be the best answer there. Do another couple of examples with you guys. These are kind of tricky, and it just takes practice and some repetition, to be honest with you, to get good at it. Example 2. We're still simplifying here. Let's do A. I have the 5th root of 16 times the 5th root of 2. Now, one thing you may recall, if I have, let's say, if I had the square root of A times the square root of B, You knew that that was the square root of a times b. You can bring them together in the same root. That goes the same for if I have the nth root of a times the nth root of b. I can bring them together under the same nth root. So that kind of comes in handy here, especially because I have the same index. Do you see that? These are both fifth roots. So I'm allowed to take the fifth root of the product 16 times 2 together, which kind of turns out to be nice because it's the fifth root of 32, which hopefully by now you're kind of getting the hang of these higher roots. Fifth root of 32 is just 2. Let's look at another one, b. Let's say I have the cube root of 108 over the cubed root of 4. This is similar to the previous example's last problem. Similarly, if you remember, if we had like the square root of a over the square root of b, that's the same as the square root of the quotient a over b. All right, so I can do that here if I have the nth root of a over the nth root of b. I can take the nth root of the quotient a over b. So what I'm telling you is this: because I have a cube root over a cube root, I can cube root the entire quotient 108 over 4. Now I think 4 goes into 108 27 times, so I have the cube root of 27, which actually turns out nicely because the cube root of 27 is just the number 3. Let's do a few more examples. Example 3. Example 3. Let's do this one. I have the fourth, let's write a first. I have the fourth root of 48. Now here the idea is I need to pull out all perfect nth powers, powers from the radical in order to simplify it truly. Okay, so there's a lot of ways of doing this, guys, and I'll show you a couple ways that I like kind of do it. First of all, 48 is not a nice perfect fourth power of anything. So kind of like a similar example or a parallel example is like if you had the square root of 20, right? 20 is not a perfect square, but we could still simplify it. We would look for perfect squares to pull out, and we'd break down 20 into 4 times 5, and we knew we can take out a 2 because the square root of 4 is 2. Well, we're doing the same thing here, guys, but we're not looking for perfect squares. We're looking for perfect powers of 4. So what I might do is start breaking down the 48. I know 2 times 24 is 48. I can't break down the 2 anymore, but I can break 24 down into 2 times a 12, right? And I kind of am stuck with these 2, so I'm going to keep writing the 2's. 12 is the same as 2 times a 6, and I can break down the 6 even further. So I'm going to have a 2 times a 2 times a 2, and 6 is a 2 times a 3. Now check this out. Really, what we can rewrite this as is the fourth root of the product of 2 times 2 times 2 times 2 times 3. Right? That, if you multiplied all that good stuff together, that's 48. Now, we do have a perfect power of 4, and if you think about it, there's 1, 2, 3, 4 2's there. Another way of writing that is 2 to the 4th times 3. So technically what I can do is I can take the fourth root of 2 to the 4th and multiply that to the 4th root of 3. But this is nice. The 4th root of 2 to the 4th is the number 2. I can pull a 2 out of this, and I'm left with the 4th root of 3. Now, I told you there was another way of looking at this, and there is, but it helps if you know a perfect powers of 4, like a much simpler looking way, and again, it's not always very obvious though, and that's why it's a little tricky to do it this way, is if you know your perfect powers of 4. You might know that 16 is a perfect fourth power of 2. So if you broke 48 into the product of 16 times 3, you're on easy street. Because 16 times 3 is 48, and then you can take the 4th root of 16 and multiply it to the 4th root of 3. And the 4th root of 16 is 2, and you'd be left with the 4th root of 3, giving you the same exact answer, but just a lot faster. Let's take a look at another one of this type. Let's look at B. Actually, let's do one that is one where we have to rationalize the denominator, which you may have remembered. If I have the 5th root of 3 over 2, guys, you have to realize this is the same as the 5th root of the numerator, 3, over the 5th root of the denominator, 2. Now, you never want to have a radical in the denominator, so you can't, let's write that, can't, if this thing will write, have a radical okay, having a hard time writing here. Can't have a radical in the denominator. So we have to rationalize. What you have to realize is this, guys. In order to rationalize this denominator, we would need to make the radicand a perfect power of 5. Right now there's only one factor of 2 inside. And in order to make it a perfect power of 5, I would need to introduce a 5th root of 2 to the 4th power. And I'll explain that in a second. But if I multiply that to the bottom, I'm going to multiply the 5th root of 2 to the 4th in the top. Now let's talk about why I did that in particular. If you think about it, since they're both in the 5th root, I can combine them, right? So let's just look at the denominator. It's going to be the 5th root of this 2, the original one, times a 2 to the 4th. Right? I can bring them together. They're both 5th roots. But now, check it out. 2 times 2 to the 4th. Don't I have really 2 to the 5th? So I have the 5th root of 2 to the 5th. Guess what that is? That's just 2. So I've changed by multiplying by the 5th root of 2 to the 4th. That original denominator became a 2. Now the numerator is maybe not so pretty. I have the 5th root of 3 times the 5th root of 2 to the 4th, which, since they're both in the same 5th root, I can bring together and multiply the 3 times the 2 to the 4th, all in one radical sign. Now, there is no perfect 5th power there, so I have nothing to pull out. I come close, I have 2 to the 4th, but that's not good enough. I need 2 to the 5th in order to pull something out. So I think that's 3 times 16, and 3 times 16 from the last example is 48. So I have the 5th root of 48, and I'm stuck with that in the top, over the number 2. Kind of tricky rationalizing with these guys. So what I'd like you to do now is try a self-quiz, and I'll write these problems out for you. These are the couple that I would like you to try. So here's your self-quiz action. Number 1, I would like you to try to simplify 6 to the 5th times 2 to the 5th raised to the negative 1/2 power. Negative 1/2 power. Number 2, you're going to do the 4th root of 48 over the 4th root of 3. Number 3, I would like you to try to simplify the 4th root of 2/9. And number 4, you're going to try to simplify the following. Let's do the 5th root of 64. And then we'll call it a day and we'll talk about it more tomorrow. Thanks for watching.